G'day everybody. In our lesson today we're going to look at sketching exponential logarithmic functions. In particular we'll look at the features of each function that we should include in a sketch, and we're going to recall and use transformations to sketch exponential and logarithmic functions by hand. So what we're looking at here is any exponential function. We've got two versions, as you can see. Most of the time we are dealing with a base that is greater than 1, so a positive value, often it's Euler's number. In this case our exponential graph looks like this. For any base it's going to go through the y-intercept at 0, 1, and it's going to have a horizontal asymptote along the x-axis, or the equation y equals 0. Occasionally we might be dealing with a base that is a fraction but positive, so a value of a between 0 and 1. In this case you'll see the graph slope like this. It's got the same asymptote and it's got the same y-intercept. For both functions, as you can see in the two graphs, the domain of these functions are all real numbers. The range, the y values of these functions are just positive real numbers. So when we think about understanding transformations and using these transformations to help us sketch graphs, it's often very handy to be able to write an equation in terms of some base function. So in our examples on this screen here, we're working with the base function e to the power of x. And I've got three examples: e to the x plus 1, another version of e to the x plus 1, and 2 times e to the x. As you can see here, if I was to write each of these equations in terms of the base function, our first equation is the function of x plus 1. In our second equation, x plus 1 itself is the power. You can see here we've swapped x with x plus 1. So we can call our second equation the function of x plus 1 in brackets. Our second equation is the base function multiplied by 2. So in terms of the base function, this third equation could be stated as 2f of x. You might be able to recall from Unit 1 and 2 what transformations are occurring on the base function for each of these three graphs. If we're adding or subtracting anything to a function, a constant value that is, we're talking about a translation that's going to be vertical. In this particular case we're adding 1, so the translation is up 1 unit. If I'm swapping x with x plus or minus a constant, that's going to give us a horizontal translation. In this case, when we swap x with x plus 1, the graph is translated to the left 1 unit. And in our third example, we're talking about a dilation from the x-axis by a factor of 2. So once we're aware of those transformations, and we're aware of what the original function looks like, or the base function looks like, we can use those transformations to come up with a very handy sketch. This type of transformation some students haven't encountered in Units 1 or 2, so we'll just talk about it now. What if we have e to the power of 2x? Here you can see we've swapped x with 2x. So we've got f of 2x. This is also a dilation, but in this case the dilation is from the y-axis. So it sort of stretches away or towards the y-axis instead of away or towards the x-axis. In this case the factor of the dilation is going to be a half, or 1 over 2. So you might want to just write this down as a little summary about the two dilations. When we can see that a function is being multiplied by some other factor, that is a dilation from the x-axis by a factor of n. When we are swapping x with nx, then that is also a dilation. In this case, it's going to be by a factor of 1 over n from the y-axis. It takes practice to recognise an equation in which type of dilation we're talking about, whether it's from x or y, and depending on how we go about it, it could be either. And here's a particular case of that point. Importantly, well, critically I suppose here, the graph is going through the origin, so it's when we're stretching it away from both axes, that point's not going to change. So if our base function is x cubed, which is this red graph here, that's the graph of x cubed, basic cubic function. The blue graph, there are two ways of looking at that. I could say that it's 8x cubed, or I could say that it's 2x all cubed. So we actually have two ways of describing the transformation of this graph here, this x cubed graph. On the one hand, we can see that it is being stretched away from the x-axis on both sides, so it's moving away from the x-axis. So we could say that it's a dilation from the x-axis by a factor of 8. We can also look at it from the point of view of the y-axis. We can say that it's actually coming closer, or compressing if you like, towards the y-axis in this direction. So as we can see here, it's the blue graph is half as far from the y-axis as the red graph. So we're saying that the dilation is from the y-axis by a factor of a half. And it's the same curve. So let's have a look at an example. I'd like you to have a go at graphing the equation y equals 2 to the power of x minus 2 minus 3. Just to kickstart, I suggest you say let f of x equal 2 to the power of x and write the equation y in terms of x. Okay. Our equation y could be written as f of x minus 2 minus 3. So reading that graph, we've got two translations, a translation to the right of 2 units, translation down 3 units. This is our base function. So let's have a look at what happens to this base function when we translate it right and down. So you can see the translation down is the most obvious one. We can see that the asymptote, which was the equation y equals 0, is now the equation y equals negative 3. And I've plotted the point 2, negative 2, because that is this point here, this original y-intercept has moved to the right 2 units, and it's moved down 3 units. So just to indicate what's happened to that point in particular, it's moved from 0, 1 to 2, negative 2. And we've got a good sketch of that equation. A lot of the time you'll be using technology, and so here's our sketch, and you can see here we've also been able to use the technology to find approximate values of the y-intercept and the x-intercept. What if we want to solve that x-intercept by hand? Here we find ourselves solving an exponential equation. So the equation y, if we let y equal 0, means that we're solving the equation 2 to the power of x minus 2 minus 3 is equal to 0. If you'd like to have a crack at solving that equation, pause the video and come back and have a look at the solution. So here you can see I've added 3 to both sides. I've taken the logarithm of both sides because I'd like to solve x when it's a power, so I've got the logarithm of 2 to the power of x minus 2 is equal to the logarithm of 3. Using our log laws, x minus 2 becomes the coefficient. Please make sure you use brackets there to show that coefficient. Another log law, that section there is going to simplify to 1, and that was the whole point behind choosing the base of 2 in the first place. and we get an exact value of x, which is the log of 3 plus 2. And it's quite okay to write the x-intercept in that way. Alternatively, we can take that expression, log of 3 plus 2, and here we've shown that we can reduce that to the logarithm of 12. So another way of writing that x-intercept in exact terms would be to say that it's the log of 12, 0. Let's take a quick look at the logarithm function. The thing about understanding transformations is that it really makes little difference what the original function looks like. It's about recognising the equation and seeing which transformations have occurred. The graph for the log of x with any base a, as long as a is bigger than 1, the base is bigger than 1, we've got a vertical asymptote, and our graph does this. It's got an x-intercept at the value of 1. Likewise, we've got a graph if the base happens to be a positive fraction less than 1, in between 0 and 1. And the graph occasionally might look like this if we're dealing with that type of expression. Looking at those two graphs, we can see that the domain of both functions is positive real numbers, and we can see that the range is all real numbers. So let's have a look at sketching the graph of y is equal to the log of 3x minus 2. Maybe to give you a kickstart here, let's use the base function f of x equals log x, because we've got a logarithm in our equation. That means we can write that equation as f of 3x minus 2. You can see here we've swapped x for 3x, and we've subtracted 2 from that function. So if you'd like to use that base function and just take a moment to produce a sketch of this equation, log of 3x minus 2, pause the video, come back and have a look. So here we go. By writing the function like this, we can see we've got two transformations. In this case, we've got a dilation by a factor of 1 over 3, or 1/3 from the y-axis. It means our log equation is getting closer to the closer to the y-axis on both sides, and it's also translating down 2 units. So our graph is going to look like this. The asymptote is not going to be any different. Our asymptote will still be x equals 0, and the curve itself doesn't look terribly different. Once we've dilated and translated it down, it still looks like a log graph, indistinct from any other. So in this case, it's probably important that we can solve that x-intercept. So let's have a look at what that x-intercept would be, or if you'd like to pause the video, let y equal 0 and try and solve x. That would be good. So here we've got, let's solve the equation y equals 0. It's a logarithmic equation. I'm using my log laws to get 3x by itself. So I've got a logarithm on both sides, introducing the log of e to the base e on the right hand side. That's so we can use a logarithm. We've got the log of e squared, and we end up with an equation, or a solution actually, x is equal to e squared over 3, which is the exact value for the x-intercept of our graph. It's important in this course to be also aware of reflections. We haven't looked at reflections today. We've got two types of reflections. When we've got a negative coefficient of the whole function, we've got a reflection in the x-axis. When I swap x with negative x, we have a reflection in the y-axis. So be aware of those two reflections when you're sketching and transforming functions. So today we've looked at how to do these sketches. We understand what features of each function we should include, asymptotes, x-intercepts, and we've been able to use transformations to sketch those functions. Thanks very much.